Folks, one of the things that you've learned in general chemistry, hopefully, is this definition of what we call an ionic and a covalent bond. That is an N, by the way. Here, I told you my writing is chicken scratch, and here is a prime example of that. All right, so we have an ionic bond and we have a covalent bond. So one of these things that you learned in general chemistry was the difference between ionic and covalent, and there is a major difference between them, and we want to talk about that difference. So ionic normally was presented to you as this concept that you have a metal and a non-metal that has came together to form a molecule. And covalent was typically all non-metals, okay? So this was this whole idea that atoms on the periodic chart really gravitate toward one side of the house or the other. So if you have a metal and a non-metal, or a male and a female maybe, this is an ionic bond. If you have all non-metals are all the same, so two guys or two girls, that would be called a covalent bond, all right? So we have both of these types of relationships that are out there in chemistry, and this is normal and it's okay, right? What we're going to focus on with organic, though, is the covalent bond. So we are going to be looking at molecules that are all made up of non-metals for the most part, all the way across the board. We're not going to bring in the other side of the house or the opposite of. We're not going to bring in the metals. Those are typically general chemistry. Those are typically inorganic chemistry if you take these types of classes. Covalent is really the field of organic chemistry. All right. Another definition that they could have presented to you when you took general chemistry is ionic means a transfer of electrons, and a covalent means a sharing of electrons. So what happens is that you have two atoms that come into the picture, and one of them says, you know what, I have too much to handle. Poof, off goes the electron. And then the other one says, oh, look, you have exactly what I need. So I need that electron, and I'm going to take it in. That is a full-blown transfer, because what happens is that this becomes positive due to its action, and this becomes negative due to its action. And guess what, folks? Opposites attract. We have a positive and a negative. When that goes on, we call this an ionic bond. That was the definition back in general chemistry. Covalent bond basically means we have an atom that comes in and another atom that comes in, and this atom says, you know, I don't really want to get rid of anything. I think that I need to keep on or hold of everything that I have. But you know what? You kind of have what I need, and I kind of have what you need. So why don't we just kind of get together and form this relationship where we can share what we have together? Okay? Think of this as a marriage, and think of this as a divorce. Ionic compounds are basically divorced. They split, they are separate. One gives up something, the other one takes it. Covalent, on the other hand, that is a nice, perfect little marriage. Storybook. Two atoms come in, two atoms live together, two atoms share everything that they have, one bank account, one house, a couple of cars, they share dinner every evening, they share breakfast every morning. That is a covalent bond. So organic compounds are made up of mostly non-metals across the board, and organic compounds share electrons. They are in a marriage together. They have what all of the others need, and they have a mutual agreement between the two that they will flip-flop that electron to whoever needs it. Think of it as the car keys, right? If you need the car this morning, take it. I'll take it tomorrow. No big deal. We'll share the vehicle. We'll share the bank account. You want to go out and go shopping? Take my checkbook. Here you go. Or take my debit card. There you go. Go take it. Go do whatever you want. Because when you get finished, I'm going to go do it tomorrow. That is a covalent bond. Well, there's another way that ionic and covalent can be defined, and this is in terms of what I'm going to abbreviate as EN. And EN, I'll tell you what that means in just a second, but EN values, if they are greater than 1.7, that's the kicker. That's the key. That's the number you want to focus on. Or if they're less than 1.7. If they're greater than 1.7, this is going to be an ionic compound. And if they're less than 1.7, it's going to be covalent. And I said compound, but it's really a bond. I'm talking about bonds here, all right? Ionic bonding is a metal and a nonmetal. Ionic bonding is a transfer of electrons. Ionic bonding is greater than 1.7 with EN value. Covalent's the same way. It's covalent bonding. Nonmetals coming together kind of get stuck. Covalent bonding, they share electrons. Covalent bonding, the EN value is less than 1.7. So I'm going to go back to the periodic chart, and I need to go to this periodic chart and clean it off. So that way you'll know exactly where metals and nonmetals are going to be located. Okay, so on this periodic chart, you are going to find an area that's pretty important, and it starts over on the P block. And the P block is going to be right here at boron. So there we go. And what I'm going to do is I'm going to draw a staircase that goes down the periodic chart this way. Okay, so there we go. The reason that I drew the staircase is because anything to the left of this staircase is typically regarded as a metal. Anything to the right-hand side of that staircase is typically regarded as a non-metal. And anything on the staircase, boron, aluminum, silicon, germanium, arsenic, antimony, tellurium, polonium, all of those are typically regarded as metalloids, but I'm going to leave that off because that's not really important for us right now, with the exception of aluminum. So this is a way that we can determine if a compound is ionic or if a compound is covalent. So for example, let's say I have NaCl. Na is over here to the left. That's a metal. Cl is over here to the right. That's a nonmetal. So this is an ionic compound. That means that Na and Cl are divorced. It means that Na is a full-blown positive, Cl is a full-blown negative, and those opposites do attract. It does keep the molecule together, but they kind of have a dysfunctional relationship because of that. Okay? NaCl is an ionic bond. Okay, well, what if we had something like CO2? Well, carbon is here to the right. Oxygen is there to the right. Both of those are nonmetals. So therefore, this would be regarded as a covalent bond. That means a transfer of electrons does not happen. Carbon and the oxygens come together, and they all share the electrons. They share what they have with each other. And they form this relationship together, and this is going to be regarded as a covalent bond. This is the difference between those two definitions. All right? Okay, well, what about water? The reason I'm going to bring that up is because this is kind of tricky. A lot of people would look at this and they would say, oh, Oh, okay. So hydrogen is over here to the left and oxygen's over there to the right-hand side. So we have a metal and a non-metal. So I'm going to call this ionic. That's wrong. It's not ionic. This thing's covalent. But wait a minute. You just told me if there are things to the left, then that's called a metal. Hydrogen's a metal, so why isn't this covalent? Well, hydrogen is the exception here, folks. You're going to see this often. This exception, well, it's mainly due to hydrogen, and we're going to treat this as a non-metal anytime we make these decisions. Because hydrogen, in this case, kind of needs to be fitting right in there. Just like helium had a flip-flop a while ago, we always see problems out of these two. And here's another reason where that happens, or another way that that happens. So water is a covalent molecule because hydrogen is regarded as a non-metal, not a metal. So therefore I have all non-metals here, and that gives me a covalent structure. FeCl3. All right, so what about this guy? Well, if I go to the left and I find Fe, there we go. This is a metal. It's automatically ionic. I don't really have to do anything else to it. There is a metal involved, and that metal automatically makes it ionic. That means that this will do a transfer of electrons. It means that iron will be fully positive and the chlorine will be fully negative in order to make this attraction happen. I'm not really said too much about that En value though yet, have I? And that's because that's to come. Just bear with me. What about SO2? Okay, well, S over here to the left, to the right, O over here to the right. Both of these are on the right-hand side, so therefore this thing is going to be covalent. It's covalent bonding. That's all there is to it. That covalent bonding means the S and the O's come together. They share their electrons with each other. There is no transfer that happens between the two. There is no full-blown charge that happens on the S's and the O's. And because of that, the dynamic of that bonding is a little bit different than the traditional ionic. Again, organic is all about the covalent bonds here. That is what we're going to be focused on for the most part. Now, what about the En value? Okay, what is this thing? What is En? Well, En is going to stand for electronegativity. That is why I abbreviate it En. Who wants to write out that word all the time? So En means electronegativity. How can I define this? Well, listen, if you read the textbook, it's going to give you this garbage, and that sentence or those two sentences probably are not going to make any sense to you. I'm going to give you layman's terms what electronegativity means. It's basically how bad the atom wants electrons. That's it, folks. It's greediness. That's all that electronegativity is. So, for instance, if I had sodium and if I had maybe carbon and if I had maybe oxygen, we can look at them and predict how greedy they are going to be. Greedy in terms of electrons. Does it want electrons really, really bad? If so, the electronegativity is very high. If it doesn't want electrons at all, then that means the electronegativity is very low because that atom is not very greedy when it concerns the electrons. The electronegativity is affected by the octet rule. Octet again means 8. So I'm going to go back to the chart and let's go through and clear some of this off of here. Goodness sakes, look at all the scribbles that we've done all over this periodic chart. By the way, you can find a copy of this periodic chart in Blackboard if you've not discovered it yet. It's in there for you. You can print off as many copies as you need and write all over them just like I do. And this is the typical periodic chart that you would see giving with a test or something like that if you had to take one in person, or if I send one to you to have you do it by hand. This is the type of chart that you'll see. So if I take a look at sodium, here we are, to the left, that has 1 valence. It's easier to lose the 1 than to gain 7. Did you hear what I just said? It's easier to lose the 1 than it is to gain the 7. Therefore, it's not very greedy when it concerns electrons. It doesn't really want electrons. It wants to get rid of them, but it doesn't want extra. So the En value for this sodium is probably going to be pretty low. If I go over to oxygen and I look here to the right-hand side, this oxygen has 6 valence right now. It's going to be easier to gain 2 than it is to lose 6. If I gain 2, I get the octet. Therefore, this thing's going to be electron greedy. It's going to want those 2 electrons in order to fulfill that octet that it needs. So this En value will probably be pretty high. And it's all driven to the octet rule. If you want actual numbers, then I can give you a periodic table that will list some of these. And here they are. Notice that over here to the right-hand side, up here at the very top, here is where your most electronegative atom is going to be. Right there, fluorine at 4.0. Over here to the left-hand side, down at the bottom, you're going to see the lowest electronegativity value. Notice the transitions are left out. Why? Because we told you the very few times do we use transition metals in organic chemistry, so who cares about them? But there's a general trend here. And the general trend is listed on this image. Electronegativity goes up as you go across, and electronegativity goes down as you go down. In other words, fluorine is going to be the highest. And if you want to use that as a starting point, as you go down from fluorine, it gets lower, lower, lower. And as you go further to the left of fluorine, it goes lower, lower, lower. I think that's an easier trend to remember than what they've stamped onto this image for you. So fluorine's the highest, and as you go lower, it goes lower, and as you go to the left, it also goes lower. So why am I bringing this up? Well, remember that En value. That En value was 1.7. That was the kicker. That was the key. So if I had NaCl, I can go to Na, which is 0.9. I can go to chlorine. Chlorine's there, of 3.0. I subtract these numbers. You'll always get a positive number here, all right? So take the absolute value if you get a negative. So 3.0 minus 0.9 is 2.1. 2.1 is greater than 1.7. So therefore, this is proof using electronegativity that NaCl has an ionic bond. Another one of those was the bond between carbon and oxygen. We said that that was covalent. I'm only going to draw one oxygen here. Well, that carbon has a 2.5, and that oxygen has a 3.5. 3.5 minus 2.5, folks, that's a 1. That is less than 1.7, which means that the bond between that carbon and that oxygen is a covalent one. That is how we use electronegativity, not position, on the chart, in order to guide us to determine if something's ionic or if something is covalent. So keep in mind, everything wants an octet. Octet basically means 8 valence electrons when it can get them, or a full set in the outer shell if it can get them. That is the driving force to determine the greediness of the atom, and that greediness can be measured, and that is what we call electronegativity. All right? So that's where this video is going to stop, and the next one we're going to continue on. We're going to keep bringing out these old ideas from general chemistry and just rehash them out one more time to give you a nice review and give you a nice foundation before we go a little bit further. So stay tuned, don't go anywhere. Come back with your notebooks. Maybe go get something to drink or something to eat. Just make sure it's non-alcoholic, so that way when you come back, you can actually pay attention and take good notes. See you then.